Example number 6 asks us to take these 4 story problems and try to set up the variables and determine what information is important. So I'm going to go through each of those for you. So for question 1, I guess it is question number 1 there, it says that there's a shepherd that lives on a straight coastline and has 500 meters of fencing with which to enclose his sheep. Assume that he uses the coastline as one side of the rectangular enclosure. What dimensions should the rectangle have in order that the sheep have the largest possible area in which to graze? So the first thing to do is set up your picture. So go ahead and draw out what you've got. Well, we have some coastline here, like that. And then we've got some fencing, and we know that it's 500 meters. And we know that it needs to be in some sort of rectangle. So what I'm going to do is just draw a generic rectangle here. Okay, and so the sheep are going to go ahead and graze in here. So just notice that we didn't have to have a fourth side because we have the coastline. Now what you want to do is you want to set up your variables. So what we're looking for, and so when you read through a problem, always look for what your end goal is. So in this case, we're trying to find the largest possible area. So we want to find the largest, which is telling us that we're going to try to find a maximum of all the possible areas we could use. Now we don't know how long each of these sides are going to be. The only thing that we know is that we have 500 meters. Okay, so this is what we're trying to determine. We know that we have 500 meters of fencing. Since we're looking for area, and we've got a rectangle, we should write down what the formula is for the area of a rectangle. So area is computed for a rectangle by taking the length and multiplying it by the width. So we'll just call this guy down here the width, this guy the length, of course. So there's another width down here, and there's another length here, but again, that's coastline, so we're not going to put fence there. We'll assume that the sheep aren't going to run into the water and drown. Okay, so what are we going to do? Well, let's go ahead and set up our equation. We only are going to have one equation here. Okay, so we need to get rid of one of these variables. Well, let's say that we use, okay, now I'm going to erase these guys here. Let's say for the length, we use some amount of fencing. Let's just call it X. So X meters of fencing. Who knows what it is? Maybe the shepherd uses 200 here. Okay. Now the question is, how much does the shepherd have left for each of these sides? Well, if the shepherd used X here and has a total of 500, then that implies that the amount left for this width and this width, so this W and this W, has to be equal to 500 minus the amount that was used for the length, because it's already gone. So in other words, 2W has to be equal to 500 minus X, or W has to be equal to 250 minus 1/2 X. So that means that this side right here has a length, because it's W, has a length of 250 minus 1/2 X. Now, what I'd recommend doing is, if you can play around with a problem, like this one's not too hard to do, I would recommend plugging in some values and just seeing what happens. So for example, so this is just some side work. If you're working on a test in this class, or actually maybe something in a physics classroom, play around with some numbers and see what happens. So we know that we have an area our area is equal to x times 250 minus 1/2 x. So in other words, the area as a function of x, the area as a function of this side length is equal to 250x minus 1/2 x squared. So the side work, let's say for example again that the shepherd uses, let's say, 300 meters for this side right here. So 300 is the x length. Well, then that would mean, if we drew that guy out, if there was 300 used here, then these sides, there's 200 left, so each of these sides would be 100. Now you can take 300 and you can plug it into this equation right here. And so, if you took 250 minus 1/2 times 300, then you would get 250 minus 150, which is 100, which is exactly what we said this side length should be. Because then, of course, this side length over here is 100. The area, when the long side is 300, is going to be equal to 250 times 300 minus 1/2 times 300 squared. It's essentially taking, if you look right here, it's taking 300 and multiplying it by 100. So if we do this math out, we have 250 times 300, so this is 75,000 minus 300 squared divided by 2, so minus 45,000, and that ends up being 30,000. So if we go ahead and we take 750 minus 45, here's our 30,000. Now we could have got this 30,000 by taking 100 and multiplying it by 300, because that's 3 with 4 zeros after it. So there's our area of 30,000 square meters again. Now, what I would advise doing is stopping the video at this point and trying a different x value. Maybe plug in 200 here. See what these sides are. See what your area is this way. Plug it into this formula and make sure you get the same number out. So I'm verifying my formula right here. And it looks pretty good. So let's go ahead and just erase this. Now what we're going to do next, in the next video, is I'm going to take this guy right here and I'm going to try to find, because my objective here is to find the largest or to maximize. I'm going to maximize this function on a certain closed interval. Okay, now this function is continuous, and so in the next video we'll discuss how to go ahead and solve that. But this is the setup right here. Okay, let's go on to, I'm gonna have to give myself some space in there, I think, too. So let's just jump onto the next page. I think I can do that. Yep. Okay. So here's problem number 2. It says illumination, or light, from a point light source is proportional to the intensity of the source and inversely proportional to the square of the distance, and my computer just shut down while I was reading that, to the square of the distance from the source to the point of observation. Given 2 point sources 10 meters apart with one source 4 times as intense as the other, find the darkest point on the line segment joining the sources.